Questions about anything? Anything?
8 months, I've never seen you send a meme.
Anything from last time? Well, today's an exciting moment because I'm going to demonstrate the maximum modulus principle for analytic functions, which is rather a unique property that they have, and it's sort of one of those things that's you could use it to prove the fundamental theorem of algebra, for example, and that's one of the problems in the homework 4, which is now up. It's a longer than average homework, and so I'm going to give you 2 weeks to do it. So it'd be even more dangerous to save it to the last minute. But it's got some good stuff on there, including show that the maximum principle implies the fundamental theorem of algebra. What the heck? That's already ridiculous. Okay. I told you we'll need a couple calculus lemmas from freshman calculus, and one is a very elementary fact that if you have h on an interval a, b, and real valued function that's continuous on the closed interval, and it's greater than or equal to 0 at all points, then it is true that the integral being 0 implies the function is 0 on AB. Okay? You can think of things that wiggle, like sine and cosine, where the integral be 0, and obviously the function's not 0. But in the case of a continuous function that's greater than or equal to 0, that's one thing you get. And the proof is very elementary. It's the kind of thing we might do in freshman calculus and wouldn't be appreciated because it requires the real mathematical definition of continuity. So if suppose that it was positive someplace, say right here at t naught, well then if it's positive because it's continuous, I would use the definition of continuity and take, could somebody close that door? I'd take, say, h of t naught over 2 as my epsilon. And I'd get a delta. Like that. And then my function being continuous, and if I use that delta, then there's this little box down here. Let's see, here's the halfway mark. Epsilon over 2. Here's the plus and minus delta. Plus delta minus delta. That integral would be greater than, let's see, the height is epsilon and the base is 2 times delta, and that's bigger than 0, and that's a contradiction. So, of course, that can't happen. Okay, and the real lemma we're going to use when I prove the maximum principle is sort of the upside-down version of that. It's that if I have h that's continuous on an interval, and it's less than or equal to m, which you should think of max, a max, well then if the integral is m times b minus a, which is what it would be if it was constantly equal to m, well the only way that can happen is if that h is identically equal to m. Okay? And so the proof would involve doing the previous lemma with m minus h in place of that h. It pops right out. And the picture proof, I won't give it again, but if the function dipped down somewhere, then you could stick in a little disk like that and see that the area would have to be strictly less than m times b minus a. Anyway, sometimes that's the way I prove it, but the baby lemma is easier to do. Questions about that? Okay, the key to this maximum principle is that the Cauchy integral formula implies the maximum principle. So the key Cauchy integral formula implies the maximum principle for the maximum modulus theorem. So sometimes I'll drop the word modulus, maximum modulus theorem or principle. But, I'm sorry, there's this intermediary thing here. the Cauchy integral formula implies an averaging property. And the averaging property is what's going to imply the maximum principle. Okay, well, let's see. It's a very simple calculation to see that we do have, I think I might have shown this at some point in the past. Let's suppose I have a circle of radius r about z naught is parametrized by z of t equals z naught plus r to the e to the it as t goes from 0 to 2 pi. And then if I have a f analytic and do the Cauchy integral formula, I would have f at the center is equal to 1 over 2 pi I integral from 0 to 2 pi. And here I would have f of z naught plus r e to the it. And in the bottom, I'd have z naught plus r e to the it minus the point z naught. So that z naught's going to cancel. And the z prime of t would be 0 plus I r e to the it. And so the z prime of t that goes right here is I r e to the it dt. Okay, that's just writing out the Cauchy integral in a parametrized form. Notice the z naughts cancel in the denominator. And then after that, the r e to the it's cancel. And even the I can be pulled out and cancel the I. And I'm left with 1 over 2 pi integral from 0 to 2 pi f of z naught plus r e to the it dt. And if I wanted to think it in terms of averaging, here's maybe a better way to think about it. I could put, this is r d theta right here. So I put an r d theta, that would be d arc length. And then in the bottom I would have 1 over r, and that would be 1 over the length times the integral with respect to arc length. So that's an averaging property. But usually I won't put the r's there. This is the ds. This is r d theta. I wish I would use d theta instead of t. But this is ds, arc length. And of course, 2 pi r is the length of the whole circle. So I'd like to think of, And a fascinating thing is, when I split f into real and imaginary parts, I would have here u of z naught plus I of v of z naught. And then when I split the integral into real and imaginary parts, it's equal to the average of u plus I times the average of v. And when and so that means that the real and imaginary parts of analytic functions satisfy the averaging property. So note, it's going to turn out that the real and imaginary harmonic functions are always going to have harmonic conjugates, and therefore we can do this trick and see that harmonic functions satisfy the averaging property. So we see that real part of f and imaginary part of f also satisfies. I'm going to be careful about it when I do it next time. Satisfies the averaging property. And that's going to imply soon that harmonic functions do too. And when anything satisfies an averaging property, that's going to imply a maximum principle for harmonic functions. And it won't be a maximum modulus, it'll be a true maximum principle. So that's a remark. Okay, so I'm going to call the first version of this, the classic one, maximum principle number 1. Here it is. Let's suppose F is analytic on a domain omega, an open connected set, if the modulus of F, that's why it's called the maximum modulus principle, attains a local max at a point z naught in omega. Sometimes maximums can be attained at a boundary point, but I mean at a point in omega. Let's see, I guess I should say what that means. Meaning there exists an r bigger than 0. I guess I'll make it an epsilon bigger than 0. There exists an epsilon bigger that can be small. That's what we're thinking about, local. This is a local thing. With the disk of radius epsilon about z naught contained in omega, and the modulus of f at z is less than or equal to the modulus in the center, that's the max, for all z. It doesn't have to be a strict max. It just has to be this kind of max for all z in that local disk. Okay, now back to the theorem. Then f is constant on omega. So if you were thinking about the graph of the modulus of a function, it kind of means there's no place where you could sit down. You'll slide off because there's no possible place to sit really. That's one way to think about it. Then f is constant on all of omega. Okay, that's the maximum principle, the classic version. Okay, the proof is going to be kind of fun. With our calculus lemmas, it'll be a snap. Let's see, suppose mod f has a local max. At z naught, and we've got this little disk about z naught contained in epsilon, contained in omega. Well, then when I do the averaging property, let's say I would have that f of z naught is equal to 1 over 2 pi the average. And this is a good way to write the average, just as good as any way. F of z naught plus rho e to the it dt for 0 less than rho less than epsilon. Okay, now let me take the modulus of that stuff. I would get that, I guess I won't take, when I take the modulus, I see that modulus of f of z naught, let's see, that's going to be less than or equal to 1 over 2 pi times the integral from 0. By the way, this is going to be my maximum m. That's the max. That's less than or equal to the modulus. This is one of our classic estimates. And that's less, let's see, it's less than or equal to m, 0 to 2 pi. This is going to be less than or equal to 1 over 2 pi times m times 2 pi. Okay, what? Because that thing is a max, so the function inside is less than or equal to m. And so that would be less than or equal to the max times the length of the interval that it's being integrated on, and it has a 1 over 2 pi in front. So they cancel. And so we see that that integral equals. So the aha is, we see that the integral from 0 to 2 pi of the modulus of f z naught plus rho e to the it dt is equal to m times 2 pi. When I put the 2 pi on the other side. And so my calculus lemma implies that the thing inside, obviously, have to say these words. I won't write them. But f is analytic. Therefore, f is continuous. And I'm composing f with a continuous function of t on the inside there. And so that composition is continuous. And if I take the modulus of a continuous function, it's continuous. So the function inside there is continuous.
Would that be less than or equal to?
No. It's equal, because look at the m on the left there. It's squeezed. It's squeezed in there, so it's actually equal to, because it's squeezed. Let's see, so this is equal to m right here. And there's the big squeeze, so it's equal to m. Okay, so my calculus lemma, number 2, implies that f of the modulus plus rho e to the it dt is constantly equal to m for 0 less than or equal to t less than or equal to 2 pi. And of course, rho is arbitrary. So, and actually, it holds for rho equals 0 too. 0 less than or equal to rho less than epsilon. So on that whole disk. At the 0 point, we know that f of z naught is modulus m. So toss that in for free. Okay. And now you might, so I've shown you the modulus is constant. And this is why that homework problem I gave you to start thinking about it. The lemma, one of those cases that's important, in fact the most important one, is that if the modulus of f, let's say f is analytic, if the modulus of f is constant on a disk, implies f is constant. There. And I'll give you the proof that once you've seen it, you realize you could do it in all 3 of those cases. So let's write, I've got f is equal to u plus iv. That means that, here's the proof, u squared plus v squared is constantly equal to m squared. Okay, if it's constant. And if you think about homework, was that homework 3? Rho of uv is going to be equal to u squared plus v squared minus 2m squared. It's going to be 0 on the on that circle. Its gradient's non-zero, and it's you can see that when you think about it, you could adapt this proof that I'm about to show you to that case. Okay, let's do the dumb case first. The case m equals 0. And of course, f is identically 0, because that means that u squared plus v squared is 0. So f is identically 0. Check. That's the dumb case. And now let's do the case m bigger than 0. Okay, let's call this equation right here star. Like the hint I was talking about in the homework on the piazza, if I take d by dx of star, I would get 2u du dx. I got to use the Cauchy-Riemann equation somehow. That's why differentiating is coming to mind. Right-hand side is constant, so I get a 0 on the right. And I take d by dy of star. I get 2u du dy plus 2v dv dy equals 0. And that's a system. Okay? And I could do two things. I could either pull out the great, what can I do? Oh. The natural thing to do is to pull out the u and the v and leave behind the Jacobian matrix. So that thing right there is I can cancel out all the 2's, and I get du dx, dv dx. Here I get du dy, dv dy. So that's like a Jacobian matrix. And right here I get a uv. And u squared plus v squared is m squared. So this is not the 0 vector. So I've got a linear system that has a non-zero vector in its kernel. That can only happen that means the matrix is singular. If it were non-singular, I could use Cramer's rule and see that uv has to be 0. Okay, so, and being singular matrix means the determinant is 0. So the determinant of that matrix is 0. I haven't used the Cauchy-Riemann equations yet. And I told you to think about red box number 1 or red box number 2 in the hint. I like red box number 1 the best because it's easier to remember. And red box number 1 is kind of sitting in the top row. And so as I've done in the past, when I was showing consequences of the Cauchy-Riemann equations, by the way, I haven't used Cauchy-Riemann equations yet, so I haven't used that f is analytic. Well, let's see, du dx is equal to dv dy, so this one is equal to du dx. Du dy is equal to minus dv dx. Okay. And look at that. That determinant is du dx squared minus dv dx squared. So that determinant is... So it's important to use Cauchy-Riemann equations somewhere. And getting rid of either the y derivatives or the x derivatives is the smart way to use Cauchy-Riemann equations. And what's left here is du dx squared plus dv dx squared. And that's equal to 0. That's the determinant. And red box number 1 was f prime equals du dx plus I dv dx. And what do we have here? We have that's the modulus of f prime squared. So the aha moment is, another aha moment, is that this is f prime squared. That's 0. That means that f prime is identically 0. So f prime is identically 0 on this little disk. Did I call it d epsilon? About z naught? Maybe I did. I think I did. So now, am I done? f prime is 0 on I want to see that f prime. I want to see. Well, f prime is 0, so it certainly is constant on that disk. Is it constant on all of omega? I guess there's two ways I could use the identity theorem here. Since f prime is constant on a disk, and that disk has a limit point, f prime is 0 on that disk, f prime would have to be 0 on the whole omega, because its 0 set has a limit point. And if f prime is 0 on all of omega, then f is constant on omega because it's connected. Proved that before. So maybe that's the smartest way to do it. So the identity theorem, because every point of the disk is a limit point of the disk, would imply that f prime is constant 0, tug on it, on omega, and that implies f is constant. And so that's it. That's the proof. Questions about that? Okay, that's a classic. I'd call that the basic version of the maximum principle. There's one that often gets applied, and it's easier to describe in the engineering courses. And so sometimes this is the maximum principle. I'll call it maximum principle number 2. And let's suppose omega is a bounded domain. It's important that it be bounded here. So it's contained in a big disk. I guess I should define it. That means that omega is contained in some big disk. Okay, so we're going to assume it's a bounded domain, and f is continuous on the closure of omega. That would be a closed and bounded set. So it's got to be continuous on and I'm going to write the closure like all topologists do, is omega closure. That's not the set of conjugates of points in omega. That's the closure. On the closure of omega. And f is analytic inside. Then this version of the maximum principle says, so that's a period, that f attains its maximum, the modulus of f attains its maximum value. So the key word here is attains its maximum value on omega closure at a point in the boundary. Of omega. Of course, if number 1, if the maximum occurs at an interior point, then the thing is constant, and it would assume the maximum at all points. But it's guaranteed to assume its maximum value at a point in the boundary, perhaps all the points in the boundary. So this means there exists a z naught in the boundary um, of omega with the modulus of f of z naught equal the max of the modulus of f on omega closure. And so consequently, one way to say the maximum principle is that the max of the modulus on omega closure is equal to the max of the modulus of f on the boundary. So those are another ways of saying it. Well, the proof is kind of a snap. F is continuous on omega closure. So let's see, F continuous implies the modulus of F is continuous. That's a simple exercise. And modulus of F is continuous on omega closure, which is a closed and bounded set. And in R2, closed and bounded sets are exactly the compact sets. A compact set. Okay, that's a theorem that you learn in some place. Math 341 or 440. Well, a continuous function on a compact set assumes its maximum. That's a famous theorem. A continuous function on a compact set assumes its max. It has a maximum value and it assumes it. Let's say at z naught. Well, there's two cases to think of right now. Trivial case is the case z naught in omega. Then maximum principle number one implies f is constant on omega. And boundary points are limit points of omega. And so, of course, by continuity, f would be constant on omega closure. By continuity. So if you haven't played games with the definition of boundary point in topology, that's something to think about. And therefore, we see that means that max is also attained on the boundary. Since the whole thing is constant. In fact, it's contained at all points in the boundary. Okay, so that case is done. And now the other case is that z naught is in the boundary. Well, in that case, we're done. Okay, so that's all there is to that. Let's see. Got some minutes to mess around with. Now you might ask yourself if there's a minimum principle. Let's see. Example. Here's a remark. Z to the n shows there's no minimum principle because it's obvious that the modulus of z to the n is 0 at the origin. Shows there is no minimum principle. For example, because there's a 0. And the function is not constant. That's obviously where the minimum occurs, and it's not constant. But if f is a non-vanishing analytic function, non-vanishing on a domain, there is a minimum principle, which is an obvious thing. There is a min principle. And it's a trivial thing to show. So the proof would be apply the maximum principle to 1 over f. Okay. Okay, now I want to have some fun with a problem, one of my favorite problems, just to illustrate sort of the power of the thing. Here's a problem. Were there any questions about anything? So the problem is I give you the unit disk, and I give you a bunch of points on it. Let's do A1, A2, A3, dot, 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 out to AN. Okay. And then I'm going to pick a Z in the boundary. And I'm going to connect all those Z's to these. This is the unit circle, by the way. The green thing is the unit circle. And then I'm going to connect the Z's to A1, A2, A3, dot, 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 AN. I'll call this D1, D2, D3, dot, 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 DN. So there's obviously a dot, dot, dot here. And the problem is to show there exists a Z with the modulus of Z being 1 such that the product of those D's, n equals 1 to capital N, of the D sub n's is exactly equal to 1. Okay. And we're going to use the maximum principle to do that. Okay.
So does the maximum principle mean that there are no, this function's homomorphic, it has no strict max?
Certainly it can't have even a local max in the interior. If there's going to be any max, it's going to have to be on a boundary point.
Like a strict, strict greater than.
So there's a kind of, so you think about, okay, when it's not constant, it's going to be a strict greater than. But when it is constant, of course, it's a less than or equal to, because it's constant. So you got to have two cases. And there will be times when we have to think about that. Let's see, somehow we want to get an analytic function to think about here. And of course the distance, so I'm thinking here, the distance d sub n is the modulus of z minus an. And so there's a natural analytic function going to be related to this thing, namely f of z is going to be a polynomial, which is the product, as n goes from 1 to capital N, of z minus an. Then the modulus, and here's the modulus. Okay, when z is equal to 1, when the modulus of z is 1 on the boundary, then the modulus of f of z would be the product of those. That's exactly the number we want. So we can guess that is going to be related to the, somehow, maybe. And this is a polynomial, so it's definitely not constant. In fact, it's a monic polynomial. It's a z to the n in front. So that's a polynomial, and it's not constant. Polynomial of degree n, greater than or equal to 1. And so, of course, it's not constant. Not constant. Okay. How am I going to do this? So where should I? It's going to attain. So it's not constant. That means its maximum modulus is going to be attained on the boundary. And there, I should say here, f of z is equal to z to the n plus the product of the a's. That'd be the constant term. Okay, so you think about where this thing is going to attain it. You want to know if the maximum modulus in the boundary is 1 somewhere, or maybe bigger than 1. And let's think about I guess you'd have to sit around and think for a while before it would occur to you. Where can I figure out exactly what the modulus is? Yeah, exactly, right. So if I sat around here and acted like I was lost, eventually somebody would think of and tell me to test the modulus at 0. The modulus at 0 is the product of the minus ANs from 1 to n. And of course those are all on the unit circle. So that's equal to 1. Uh-oh. The max, so the thing is not a constant, so that's not the max. The max has to be bigger than that. So since f is not constant, one is not the maximum modulus. So the maximum modulus is bigger than 1. Is bigger than 1, and it occurs on the boundary. That's a good idea. Yeah, that's exactly a good idea. So it occurs at some point z with the modulus of z equals 1. And Allah's idea was to think about what happens at the ANs. So if you go back to my picture, as that z moves around, when I hit an AN, it's going to be 0, right? Because that distance is 0 there. So if I slide that over to A3, then that distance d3 would be 0. And so it's 0 there. But I just showed you there's some point inside where it's bigger than 1. What comes to mind? Yeah, the intermediate value theorem. Okay, so that's the next breakthrough. Note the modulus of f of an is equal to 0, because one of the terms is 0. Let's say that W naught is in the unit circle. With W naught equal to 1 is the max. That means that f of W naught equals m, and that's bigger than 1. And now the breakthrough is to say the intermediate value theorem, because we've got a continuous real valued function. And so the intermediate value theorem from freshman calculus, or math 341, implies, let's see, so what's the continuous function I'm talking about? There exists a point on the boundary. Which in this case is z equal to 1 in modulus, with the modulus of f of z naught equal 1. Okay, the continuous function that you're going to use in the intermediate value theorem is going to be the modulus of f of e to the it. That's a continuous function, and the interval is going to be 0 to 2 pi. And that's what I wanted to get. That's kind of a fun thing to do. Sneaky way to show that your calculus facts are important. That makes sense? So there's lots of questions, exam type questions you can make of asking where an analytic function is maximum, and you know the maximum occurs on the boundary, and usually the functions are easier to evaluate on the boundary because you can do things like that. And so you can do a calculus problem on the boundary that's a one-dimensional calculus problem. It makes the problem a lot easier than doing a two-dimensional max-min problem. Anyway, any last-minute questions about anything? Well, next time we're going to talk in more detail about harmonic functions. Usually I'm tempted early on to say more things about them. For example, how to cook up a harmonic conjugate. But now that we have all these tools, the proofs will be considerably easier. And I wouldn't have wasted time explaining it using sophomore calculus. I can use what we know. Anyway, that's the story for next time, harmonic functions.
Why do we have minus 3m?
I put it on the other side. Remember, in the row in that problem was 0 on the curve.
Yep.
This curve is the circle of radius m. And when I take u squared plus v squared minus m, that makes it 0 along that curve. That's why I put 0. So in the problem, that would be the row.
Yeah.
Actually, I prefer m squared minus u squared minus v squared.